Hello, my name is Thomas Shircel. I am a Senior Regional Application Engineer at ABB. This presentation is called Demystifying Ultra-Low Harmonic Drive Operation. Let's look at the agenda for this presentation. We're going to do a quick overview of harmonics, just to make sure everybody's on the same page on what are harmonics. Then we're going to do a standard 6-pulse drive theory. This short overview of 6-pulse drive theory is needed to understand the ULH drive. The ultra-low harmonic drive, the ULH, we will do an overview of how the system actually operates. Then we will go into a detailed explanation of the ACH580 Ultra-Low Harmonic Drive and how the active front end operates. This will be a detailed explanation using very little math, but it will help you understand how an active front end drive actually operates. In this part of the presentation, we're going to do a general overview of harmonics. A generator produces a 60 Hz sinusoidal voltage and current to the distribution network. In an ideal case, the current in the AC grid is a pure sine wave and does not contain harmonics. In reality, the current deviates from this pure sine wave and contains harmonics. As shown here, this is a pure sinusoidal waveform. It could be voltage or current waves. The form does not contain any harmonics. In this waveform, as a voltage form or a current waveform, it deviates from the sinusoidal waveform and contains harmonics. It is a repeating waveform, but is no longer a sinusoidal waveform. So let's take a look at what are harmonics. Let's look at the fundamental frequency of 60 Hz. We are going to add multiple harmonics to our 60 Hz here, and we're going to build up a new repetitive sine wave. So we'll add the fifth harmonic of 300 Hz, and as you can see from here, that in the center, it pushed the voltage up, on the sides, it pulled the voltage down. Now we have in the black a new waveform. This waveform is repetitive, therefore it's two frequencies, 60 Hz plus 300 Hz, the fifth harmonic. So if we add the seventh harmonic, which is 420 Hz, you can see that the waveform has been altered a little bit more. We can continue on with it by adding the 13th harmonic, 780 Hz, and the 25th harmonic of 1500 Hz. Now we have a repetitive waveform that is no longer a sine wave, and it contains multiple harmonic frequencies. When we look at harmonics, we are looking in the frequency spectrum with the different harmonic frequencies on the x-axis and a percentage compared to the fundamental frequency on the y-axis. Total harmonic distortion, the THD, is a value represented by the total amount of distortion in a given signal. It is expressed as a percentage of the fundamental. The ratio of the root mean squared of the harmonic content is considering the harmonic components up to the 50th order, as expressed as a percentage of the fundamental. As shown here, we have a 6-pulse drive, and you can see the dominant percentages on the 5th, 7th, 11th, 13th, and so on for harmonics that are being created by the drive. Harmonics should not be confused with high-frequency radial interference. The 50th harmonic in a 60 Hz system is only 3 kHz. 60 Hz times 50 equals 3000 Hz. Harmonic voltages and currents are low-frequency phenomena and are conductive onto the power line. When we talk about harmonics, we need to break harmonics down into two different categories. One category is voltage distortion, and we call it THD, the small v, and current distortion, THD with an I. Voltage distortion is a distortion of the voltage waveform. It's mostly noticeable at the top and bottom of the waveform. The voltage waveform can come flat top. Current distortion is a distortion of the current waveform. It's mostly notable by drawing current in short bursts, as opposed to continuously. Power line harmonics are not high frequencies in megahertz or gigahertz, and they don't radiate long distances through air. The harmonics are conducted on the power lines. On the left here, we are showing a three-phase voltage waveform. If you look at the waveform, you see that it's not a sinusoidal waveform. You can look at the tops. The tops are flattened out on each one of the phases. This is a sign that we have a certain amount of harmonics that are inside the waveform. On the right here, we have a three-phase current waveform. This current waveform is a waveform from an input of an actual drive. For a 6-pulse drive, one of the effects is we have a double humping of current. Current is being drawn in gulps. As you go through each one of the phases, we see a gulp and a gulp of current going into the drive. This current waveform contains harmonics. Let's talk about linear and nonlinear loads. Linear loads, such as incandescent light bulbs, electrical heaters, or three-phase motors, do not create harmonics. Nonlinear loads produce harmonics, and the most common sources in HVAC are electric commutated fans, EC fans, VFD-driven fans, pumps and compressors, photocopies, PC, domestic appliances, uninterruptible power supplies, and LED lighting. They all create harmonics. They are nonlinear loads. Even if the relative portion of harmonics is created by the VFD is low, the absolute amount can be big. The more items that are creating harmonics can total up to a large amount of harmonics. Some buildings, such as data centers and hospitals, operate loads that are susceptible to harmonics and at the same time generate harmonics. For reviewing harmonics, we are going to start with the standard 6-pulse drive and how a 6-pulse drive creates harmonics. For a standard 6-pulse drive, we will be using the ABB ACH580 standard drive as our example and our model for the next few slides. Let's see what happens inside of a 6-pulse VFD. We'll apply 460 volts, 60 Hz to the front of the drive. The rectifier, which is a 6-pulse diode bridge, it contains 6 diodes to rectify 3-phase input. That 6-pulse diode bridge converts the AC input to a DC 650 volt to charge the DC bus. The inverter, which has IGBTs, creates a new output voltage and a new output frequency through the use of pulse width modulation. By creating a new voltage and a new frequency, we can control the speed of a motor and the torque on the motor. This will be an example of a standard 6-pulse rectifier. We have an input voltage coming in, 460 volts. If you look at it, you have about 650 volt peak on a 460 volt line. Now the full wave rectifier rectifies that input, so now we basically have what you see here, your rectified voltage. And if you add a rectified voltage going to a resistive load, you expect your DC current to follow the voltage, but we don't. We are charging up a set of capacitors. Now, if the capacitors charge to the peak voltage, otherwise we have no load, then the system is now idle. Nothing happens. But as the drive is running the motor, it pulls the DC bus voltage down. When the DC bus voltage drops below the peak voltages of the rectified AC coming in, what happens is we get spikes of current. So whenever the voltage exceeds the DC bus, suddenly we have a spike of current coming in to the drive. This spike of current is a nonlinear load, and that's why we call them nonlinear loads. Let's look at the input waveform for a 3-phase current distortion on a 6-pulse drive. What we see is what we call a classic double humping. This double humping is occurring because you're looking at one phase on the input of the drive. Obviously, this is not a sine wave and contains a lot of different harmonic frequencies. Now, why would you have a double hump? The reason why is because when you're looking only at one phase on the drive, the diode bridge is still dealing with all 3 phases. And because you're looking at one phase, the phases around it, you will find out you have a differential voltage. Each time the voltage exceeds the actual voltage on the cap bank, current flows. Over here on the right, we are showing an actual scope view of the input of a drive. Now let's take a look at ultra-low harmonic drives. We are going to use the ACH580 ultra-low harmonic drive as an example, and we're going to look at how an ultra-low harmonic drive operates and creates low harmonics on its input. VFD is a variable frequency drive. ULH is ultra-low harmonic. AFE is active front end. LSU is a line supply unit. INU is inverter unit. LCL filter. That is an inductor, capacitor, inductor filter. PF is power factor, and PWM is pulse width modulation. In this presentation, we are going to be looking at the ABB ACH580 Ultra-Low Harmonic Variable Frequency Drive. The Ultra-Low Harmonic Variable Frequency Drive is able to control your motor as a drive, and it also is a low harmonic solution for your system. When looking at an Ultra-Low Harmonic Drive, we start off with an LCL filter. We have our line supply unit. The LCL filter and line supply unit create the active front end, the AFE inverter/converter. We have our DC bus and an INU inverter unit to control the motor. Let's take a look at what happens inside the ULH variable frequency drive. We start off with a 460 volt, 60 Hz line. The active front end inverter converter consists of a LCL filter and an LSU line supply unit. The line supply unit uses IGBT technology to create a pulse width modulated voltage at 60 Hz. This pulse width modulated voltage is used to determine what the charge will be on the DC bus. The DC bus is charged up to a DC bus voltage. That voltage is maintained by the line supply unit. The inverter unit is used to create a pulse width modulated output. This pulse width modulated output creates a new voltage and a new frequency in order to control the motor. The inverter unit is the same type of inverter unit that is used on a 6-pulse drive. Let's talk about the LCL filter, an inductor, capacitor, inductor filter. The LCL filter is integrated with the ACH580 drive. It has a 3% grid-side reactor, a capacitor network, and a 6% boost inverter reactor. The LCL filter reduces the line notches that are produced during the operation of the line supply unit. The LCL filter is tuned to mitigate line distortions caused by higher-end frequencies. The inductors in the filter also provide impedance between the LSU, protecting the active front end from external existing line harmonics. The line supply unit uses IGBT technology. The IGBT switching is to supply energy to the drive, and the IGBT switching can be used to regenerate energy from the drive. The IGBTs control the magnitude and direction of the current and the power factor created by the drive. Looking at the LSU line supply unit, if the IGBTs are kept off, the rectifier acts like a regular 3-phase 6-pulse diode bridge. The LCL filter adds about 9% impedance, causing a voltage drop across the filter, reducing the DC bus voltage that may be needed at full load. If the drive was to run in diode mode, it would create harmonics as if it was a 6-pulse bridge. The ACH580 ULH drive does not run in diode mode, but the diodes are an integral part of the line supply unit. Let's look at the ACH580 ULH waveforms. On the line supply unit is using pulse width modulation to create a new voltage, and that creates a frequency matching the frequency of the input of the drive. We look inside the filter, we see that the pulse width modulation has been removed from the actual voltage being created by the line supply unit. And at the input of the system, we see that there's very little voltage distortion at all on the line side created by the active front end drive. Let's do a review of the ACH580 Ultra-Low Harmonic Drive. The LCL filter is integrated with the ACH580 drive. The LCL filter reduces line notches that are produced during the operation of the line supply unit. The inductance of the filter also provides impedance between the line side unit and the line. The line supply unit and the LCL filter make up the active front end inverter/converter. The line supply unit uses IGBT technology. The IGBT switching to supply energy from the drive or to regen energy from the drive. It controls the magnitude and direction of current flow and the power factor. We have a DC bus. The line supply unit controls the voltage on the DC bus. We have our INU, the inverter unit. The inverter unit uses IGBT technology. The INU creates a new voltage and frequency to control the motor by creating a pulse width modulated output. In this next part of this presentation, we are going to look at the ultra-harmonic drive and start to look at how the drive charges its DC bus, how it creates a DC bus boost voltage, and how it keeps unity power factor in place. So let's talk about direction of flow. Let's say we had 2 power supplies and a resistor. So looking at a DC power supply, relative voltage magnitudes and resistance determines the current and magnitude and direction of power flow. If the magnitude of the current from E1 to E2 depends on the voltage difference between the resistor, between the 2 power supplies. For example, if E1 is 14.4 volts and E2 is 12.9 volts, the direction of power would be from E1 to E2. If R is 0.01 ohms, we can calculate out that E1 to E2 would come out to 150 amps. Let's look at AC power flow for an example. Relative voltage magnitudes and phase angles determine the current, magnitude, power factor, and direction of power flow. The active front end is similar to 2 voltage sources connected in parallel with a reactor between them, as shown on the right. The active front end is a voltage source, like the inverter unit is a voltage source to the motor. It can create a voltage where the magnitude and phase angle can be controlled. The line voltage is fixed with respect to its magnitude and phase angle and is used as the reference. So what controls the current through a reactor? Let's talk about AC power flow across an inductor. When there's a voltage across the inductor, the current magnitude will be equal to the RMS voltage divided by the inductance impedance, shown here. It'll also have a phase angle of negative 90 degrees. The current flowing through an inductor will lag voltage across it by 90 degrees, as shown as a phasor plot in the lower left corner. So we have a voltage and a lag of 90 degrees in current going through the inductor. Let's take a look at the AC power flow across an inductor. This shows the voltage and current in respect to time, where current is lagging the voltage by 90 degrees. If you look at the voltage right here, we peak out right here on our waveform, and if you follow the current, the peak doesn't occur till here, 90 degrees later. If we look at our phasors, we have our voltage phasor, and at a 90-degree angle, we have our current phasor. This is important because we are going to use this for the rest of our slides. So AC power across an inductor, by adjusting the voltage and the phase angle, you can control the current and the phase angle, beta. So we have a fixed voltage and a fixed phase angle. That is the line. The inductor is fixed. The inductor creates a 90-degree phase angle and from voltage and current, and that's between the AFE and the line. The active front end is adjustable. We can adjust the voltage and adjust the current phase angle of the active front end. This allows to determine if we have power going from the line to the active front end, or if active front end brings power from the active front end out to the line. By controlling the voltage and the theta, we can control the magnitude and direction of the current and the power factor, which is cosine beta. Let's take a look at the voltage of the active front end compared to the voltage of the line and the phase angle of the active front end to the line. So if we have the voltage of the active front end at 100% of the voltage of the line with a 0 phase angle, the power factor is equal to 1. As we see on our diagram here, the voltage of the line and the voltage of the active front end are equal to each other. They're in phase with each other, and therefore no current is flowing. So what would happen if we change something? Let's change the voltage of the active front end to 90% of the voltage of the line and leave the phase angle as 0. This will be a lagging power factor. If we come here and look at this, the voltage of the line is in blue, the voltage of the active front end is in green, and the current is being shown in orange here. In phasors, the voltage of the line has not changed. The voltage of the active front end is now 90% of the voltage of the line. Therefore, we now have Vx. Vx is the difference between the voltage of the line and the voltage of the active front end. Because we're going through that reactor, now Ix is a 90-degree phase shift. So current is lagging by 90 degrees. All right, let's get back to normal again. We'll have our phase angle at 0 and our voltage of the active front end at 100% of the voltage of the line, and power factor is back to 1. If we look at both phasors, they're not shown on top of each other because they would be like the sine waves on top of each other. I've showed them a little bit separate from each other, so the voltage of the line is equal to the voltage of the active front end. Now let's change. We'll leave the phase angle at 0, but we'll bring the voltage of the active front end to 110% of the line voltage. And this means its power factor is leading. So when I look at this in green, this is the active front end, the AFE's voltage, and in blue is the line voltage. They're both in phase with each other, and what we have is we now have a leading current. Okay, current shown in orange. So the current is actually leading by 90 degrees. When we look at our phasors, we see the voltage of the active front end is higher by 10% than the voltage of the line. Therefore, Vx is now pointed into the line voltage, and Ix is pointed up at 90 degrees. Let's take a look at our active front end and have a phase angle of negative 17 degrees. The voltage of the active front end is going to be 100%, and the power factor that we're going to result in will be a 0.956 lagging. And now we're looking at our voltage for the active front end and the voltage for the line. The voltage for the line is in blue, and the voltage for the active front end is in green. Phase angle of negative 17% shows the voltage of the active front end lagging the voltage of the line. The current results is going to be shown as a lagging current. So how does this look in phasors? We're going to connect the phasors together at a common point, and you see the voltage of the line has not changed, and it's in the horizontal plane. And at a 17-degree angle, negative 17 degrees, the voltage of the active front end is creating a triangle. The difference is Vx. Vx is from the voltage of the active front end to the voltage of the line phasor. At a 90-degree angle from Vx is Ix. If you look at this, Ix is continuing on with the voltage of the active front end in the same phase direction, not the voltage of the line phasor. This is a 0.956 lagging scenario. So how do we correct for this? If we leave our phase angle at negative 17 degrees and change the voltage of the active front end to 105%, we can line up our power factor. So let's look at this here. In blue is the voltage of the line. The voltage of the active front end is 105% of the voltage of the line, so it's a higher voltage. It's lagging by negative 17 degrees, but the results are what happens in the phasors. When we look at that, the voltage of the line has not changed, but increasing the voltage of the active front end has created a Vx. That's 90 degrees to the voltage of the line. And what happens to the current? From the difference in voltage, the current is now in phase with the line voltage. At this point here, the line voltage and the current are peaking at the same time. The power factor is now 1. So by changing the voltage and the phase angle of the active front end, which is recreating a new sine wave, we control the difference in voltage between the line and the active front end, and we control what happens with the current, how much current flows, and what the phase angle of the current is, which controls the power factor. Now let's take a look. We're going to leave our phase angle at minus 17 degrees and move our active front end to 110% of the line voltage. The power factor is going to be leading now. So let's take a look at what we see here. We've increased the voltage on the green, which is the active front end voltage, and we left the line voltage at the same point where it was. And what we're having now is the phase angles. This is going to cause the current to be leading the line voltage. Let's look at the phasors and how this happened. The line voltage has not changed. We've increased the voltage on the active front end. This has caused a new angle to occur for Vx, which causes Ix at a 90-degree angle from Vx to be pointed up from the line phasor. This pointing up created a leading power factor. If we bring it back down to 105%, power factor will reduce back down to 1. And over here we're showing that reducing the active front end voltage, we now line things back up where the current is in phase with the voltage of the line. And that makes power factor equal to 1. Now we can bring ourselves back down to unity again. So V line and the V active front end are both in sync with each other. If you want to regenerate to the power grid, we basically just change our phase angle to plus 17 and our active front end to 105%. By doing this, our active front end is ahead of phase from the line. That causes the current to flow from the active front end to the line, as shown here. And we are staying at a unity power factor. In this diagram, we are looking at the voltage of the active front end versus the voltage of the line compared to the degrees of the phase angle to maintain unity power factor. In this vector loci, we are looking at what happens when you go from motoring mode to regenerative mode compared to the phase angle and the voltage of the active front end. As you change your phase angle and increase it, you have to increase your voltage of your active front end to keep unity power factor, and the amount of current that flows increases, depending on which way you are motoring or regenerating. Let's take a look at actual active front end waveforms in motoring mode. The line voltage is in blue, the line current is in red, and the active front end voltage is in green. The voltage shown are line and neutral voltages. That's why the active front end waveform appears to be a 3-level pulse width modulated waveform. So when in motoring mode, the active front end voltage lags the line voltage slightly and has the correct magnitude to cause the line current to be in phase with the line voltage, so power flows from the line to the drive. So as we look here, what's happening is in blue, you have your line voltage. And this pulse width modulated from the active front end is actually lagging a little bit from the line voltage. That's causing the current to flow from the line into the active front end. The current is in sync with the line voltage. Let's take a look at regenerative mode. In regenerative mode, the active front end voltage is shifted slightly to the left of the line voltage, leading it. So if you look right here, here's your line voltage in blue, and your active front end voltage, which is this pulse width modulated voltage, is actually a little bit to the left peaking of the line voltage. It has the correct magnitude and the correct phase angle to have the current 180 degrees out of phase from the voltage. So power is flowing from the drive out to the line. In this case here, we're regenerating power from the AFE to the line. Looking at the AFE active front end, the combination of the line supply unit and the 6% boost inverter reactor removes low frequencies by not creating them. These are frequencies less than 1 kHz. The LCL filter removes higher frequencies greater than 1.2 kHz. Power factor is defaulted at unity, but it is adjustable from 0.85 leading to a 0.85 lagging. The active front-end drives are less affected by line imbalances compared to other low harmonic solutions. Talk about the active front end and what controls the DC bus voltage. A question we need to ask is, after reviewing the vectors and the phase angles, what is missing? In order to correct the power factor, the voltage of the active front end must be higher than the voltage of the line. So the voltage of the cap bank needs to be higher than the voltage of the line. We advertise that the drive can support full voltage to the motor with a low input voltage. How is this done? When you're looking at the system, the line reactors add about 9% total reactance to the system. Therefore, there's a voltage drop across the line reactors, and that will not help increase the voltage of the cap bank. If you look at the capacitors in the actual filter, if the drive was not running, the capacitors would cause a leading power factor, and this could support a higher voltage than the input of the drive, but that's not the scenario either, because when the drive is running, the cap banks and the inductors are busy and do not support the leading power factor. The overall function of the active front end is to maintain the voltage on the DC bus caps by controlling the current from the transformer. The average current on the DC bus caps is the difference between the current in the active front end and the current on the inverter unit going to the motor. Normally, I cap is equal to 0 because the active front end and the inverter unit are equal to each other. For capacitor, voltage is controlled by the current flowing through the capacitor. If the load increases, the voltage in the cap decreases, and the active front end changes its phase angle to increase the active front end and bring the cap's voltage back up to normal. So by increasing the current on the active front end to exceed the current of the inverter unit, now current must flow through the capacitors. By flowing through the capacitors, the capacitance voltage increases. If the load decreases or reverses, the voltage of the capacitors increase, and the active front end changes its phase angle to decrease or reverse the active front end and maintain voltage on the capacitor. The active front end controls the line current. The DC bus voltage is no longer tied to the peak-to-peak, line-to-line voltage. Let's look at what controls the DC bus voltage. The LSU has a set of 6 diodes. If the IGBTs are kept off, the rectifier acts like a regular 6-pulse 3-phase diode bridge. The diodes cannot be turned off if the DC bus is below the input voltage the diodes pass current. To answer the question how the active front end creates a higher voltage to charge the cap bank up, the active front end acts like a boost converter. Step 1 of a boost converter is to create a line-to-line short through the inductors. The lower IGBT is turned on, creating a line-to-line short through the IGBT and up to the diode between the top 2 phases. The current in the reactors are increasing, storing the energy in the reactors. Only the reactors are limiting the rate of rise of current during this period of time. So we cannot keep the IGBTs on for too long, and during this time we are building them storing energy in the 2 line reactors. Step 2, the IGBT is turned off. The energy stored in the reactor is pushed into the bus capacitors through the diodes, following the path shown. The reactor energy is charging the DC bus capacitors. A 6-point boost reactor located closest to the active front end is needed to allow the active front end voltage to work against the line voltage. So let's take a look right here. Blue is the DC bus cap voltage, red is the current in the reactor, and green is the IGBTs being turned on and off. As the current in the reactor starts to drop, we turn an IGBT on, creating the short, pushing the current back up. If you look, this is all being done in nanoseconds. We turn the IGBT back off, that extra energy is now pushed back into the DC bus, and we turn it back on. We continue doing this on all 3 phases with the 6 IGBTs. Let's review the ACH580 Ultra-Low Harmonic Drive with an active front end. The line voltage is the source. It has a fixed voltage and a fixed phase angle. The active front end voltage source has adjustable voltage and adjustable phase angle. Between the line voltage and the active front end voltage, we have a line reactor. The line reactor causes a 90-degree phase shift between voltage and current. So our input voltage is fixed. The active front end pulse width modulation can be manipulated to adjust the voltage in comparison to the input line voltage and adjust the phase angle in comparison to the input line voltage. When we look at the input line voltage phasor and the active front end voltage, we can determine the voltage X. At voltage X, if it's at 90-degree angles to the line voltage, the current will be in line with the line voltage. At this point, we have unity power factor. So by manipulating the voltage and the phase angle of the active front end, we can manipulate the current and create unity power factor. ACH580 Ultra-Low Harmonic Drive Overview. The ACH580 Ultra-Low Harmonic Drive has an active front end with a built-in LCL filter and a line supply unit that controls the voltage to the cap banks. The inverter unit creates a new voltage and frequency to control the motor by creating a pulse width modulated output. The inverter unit is the same as the inverter unit used on an ACH580 6-pulse drive. The active front end can control the current entering or leaving the drive, producing little harmonic distortion on the line. The total harmonic current distortion is averaged less than 3%. The drive controls the DC voltage to ensure full motor voltage even when the supply voltage is below nominal. The drive adjusts its current waveform to be in sync with the voltage waveform. The displacement power factor is unity. This concludes this presentation, Demystifying Ultra-Low Harmonic Drive Operation. We have reviewed harmonics, 6-pulse drive theory, and ABB ULH drive theory. For more information on innovative ABB products and solutions, please contact your local ABB representative or visit our website at www.new.abb.com. My name is Thomas Shircel. I'd like to thank you for watching this video.